Hi, it's Professor Jones again, here to talk about Section 2.2, more on functions and their graphs. Objectives of this section are to identify intervals on which a function increases, decreases, or is constant, use graphs to locate relative maxima or minima, identify even or odd functions and recognize their symmetries, understand and use piecewise functions. Let's look at increasing intervals of increase, decrease, and constancy for a function. And let's look at how we actually define this. A function is increasing on an open interval I if f of x1 is smaller than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. What this will look like graphically is that the function is going uphill. A function is decreasing on an open interval I if f of x1 is greater than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. And what this will look like graphically is that the function is going downhill. A function is constant on an open interval I if f of x1 equals f of x2 for any x1 and x2 in the interval. And I want to point out here that intervals of increase, decrease, and constancy are always open intervals. So those intervals will never include the endpoints. So let's look at an example of this. We want to state the intervals on which the given function is increasing, decreasing, or constant. So if we take a look at this function, we see that from x's that are in the negative realm, so in other words, from negative infinity to x equal -1, the function is increasing. So notice how it's going uphill. And you're always moving from left to right when you're trying to determine this. From 1 to infinity, the function is also increasing. Okay, so those are the two intervals where the function is in. Okay, so on these two intervals, from negative infinity to -1, and from x equal 1 to infinity, the function is increasing. And notice that when we give the intervals of increase and decrease, we're giving the x values for which these things happen. Now, if we look at the interval from -1 to 1, we see the function's going downhill, so it's decreasing on that interval. Let's talk about the definitions of relative maximum and relative minimum. A function value f of a is a relative maximum of the function f if there exists an open interval containing a such that f of a is greater than f of x for all x not equal to a in the open interval. So in other words, when you talk about a relative maximum, you've got to be able to surround the location of this relative maximum on either side from the left and the right side. So you've got to be able to work with an open interval, as the definition says. So this will look like a little mountain. It may not be the actual highest point on the graph, but in its neighborhood, quote unquote neighborhood, it's the highest point. So a function value f of b is the relative minimum of f if there exists an open interval containing b such that f of b is less than f of x for all x not equal to b in the open interval. So again, you've got a relative minimum if in a neighborhood the function is smaller, has a value which is smaller than all other values in that region or neighborhood of the function. So let's look at an example of this. Let's identify the relative maxima and minima for the graph of our function f. So notice that right here at x equal -1, we have a relative maxima, or maximum. Maxima is plural. Maximum, there's just one relative maximum here, and one relative maximum for the whole function. Now notice that's not the highest point of the function, because notice the function continues indefinitely toward infinity, or increases without bound. So this is not the absolute highest point, but in this neighborhood it is higher than all other points in this little region of the graph. And notice this has to be true on an open interval. Okay, so at x equal 1 we have a relative maximum. And I mean at x equal -1. It seems like I said 1, but I meant to say x equal -1 if I didn't say that. And then at x equal 1, we have a relative minimum. So notice that in this neighborhood, this is the lowest point. It's not the lowest point absolutely on the graph, but it is the lowest point in this region. So f has at x equal -1 a relative maximum, and notice the actual maximum is the y value of this point, which is something less than 5 but greater than 0, and f has a relative minimum at x equal to 1, and that actual minimum is some value, it looks like between 0 and -5, between -5 and 0. So we would need a little more information to be able to determine what the actual extreme values are here. Notice that the relative maximum happens at x equal -1, but that value that actually is the relative maximum is the y value. Here the relative minimum happens at x equal 1. The y value of this point would be the actual relative minimum. All right, let's define even and odd functions. The function f is an even function if f of -x equals f of x for all x in the domain of f. The right side of the equation of an even function does not change if x is replaced with -x. So in other words, if you replace x with -x, the y value remains the same when a function is even. The function f is an odd function if f of -x equals -f of x. So for all x in the domain of f, every term on the right side of the equation of f of an odd function changes its sign if x is replaced with -x. Another way to say this is, when a function is odd, if xy is on the graph, so is negative x, negative y. So let me give you an example. If I have an odd function that has the point 1, 2 on its graph, then the point -1, -2 has to also be on that function's graph. Similarly, if a function is even, if xy is a point on the graph, so is -x, y. For example, if 1, 2 is a point on the graph of an even function, so is the point -1, 2. So let's look at an example where we want to identify even or odd functions. So our function is h of x equals x to the 5th plus 1. We want to know, is it even, odd, or neither? Well, our test is to replace x with -x. So that if I'm trying to determine evenness or oddness, I'm going to replace x with -x. So I not only replace the input x with -x, but all other occurrences of x get replaced with -x. So notice that -x to the 5th power is, so the 5th power of -x is probably the way I should say this, plus 1 is equal to -x to the 5th plus 1. So the thing to note here is that this is not the same as h of x. Okay, so in other words, you've got 5 negative signs. 4 of them pair up. So in other words, you'll have one left over negative. And h of -x is different from h of x. So that means the function's not even. Now, notice that if I were to multiply h of x by -1, I would get -x to the 5th minus 1. And remember, h of -x was -x to the 5th plus 1. So the point here is that h of -x is not the same as -h of x. So that means the function is not odd, which means the function is neither odd nor even. An even function satisfies f of -x equals f of x, and its graph is symmetric with respect to the y-axis. So whatever is on one side of the y-axis for an even function, the mirror image of that is on the other side of the y-axis. An odd function will satisfy f of -x equals -f of x, and its graph is symmetric with respect to the origin. So whatever is in quadrant 1 on an odd function, the mirror image of that will be in quadrant 3. Whatever is in quadrant 2 with an odd function, the mirror image of that will be in quadrant 4. A function that is defined by 2 or more equations over a specified domain is called a piecewise function. And we will look a little bit more at these in another video where we look at some examples of the problems.